Hello everyone, welcome to final recitation session for Water Resources Engineering. This is week 15, and this week we will have 5 different aquifer related questions. So let's get started with the first one, 7.3.5. Here we have a confined aquifer with a transmissivity of 500 square meters per day and a storage coefficient of 0.0005. We have two wells, well 1 and well 2. And they completely penetrate this aquifer and will be pumped at constant rates of 600 cubic meters per day and 1400 cubic meters per day. So let me write that information. We have 600 and we have 1400. And here we have an information which says the pumping will start in both wells at the same time. This is important because in next questions we will see different setups for these pumps. And we have an observation well, and it is located 400 meters from well 1 and 500 meters from well 2. So how long can the two wells be pumped without exceeding a 1 meter drawdown limit in the observation well? And at that limit, what is the drawdown contribution of each well? So in this question, basically, it says we need to find the past time that causes a drawdown, which is equal to 1 meter, so that the drawdown from both wells should be equal to 1 meter. So this will say that once these pumps started pumping, and since they started at the same time, after some time, we will see that the drawdown is at 1 meter. So we just need to find that duration. So for this, we have some basic equations, and we will have some functions such as well function here. So let's get started with the solution. Here, let me draw a basic sketch. So here we have well 1 and we have well 2. And they have some distances from observation well. So R1 is 400 meters and R2 is 500 meters. So let me add this. And also we have a storage coefficient and transmissivity as 500 square meters per day. So we are going to use 3 different equations. And this gives drawdown. This is the dimensionless parameters. And this is the well function. Okay, so to find the drawdowns from each wells, we have this table, and you can create this using Excel or some other spreadsheets. So basically, we will try to find total drawdown is 1 meter. So we will try different days, like 1 day, 2 day, 3 day. And finally, we will get this value. And as I mentioned during the explanation of the question text, we need to find how many days or how many hours passed to find this total drawdown as 1 meter. So let's get started, for example, with this one. So the t is 1, and we need to find u, because after we find u, we will be able to find the well function, and after that we can calculate the drawdown at this time. So u is equal to r square s for t and time. So since this is well 1, the r, which is the distance, is 400 meters square, times the storage coefficient is 0.005. We have 4, we have transmissivity as 500, and finally we have t, which is the time, and it was 1. So from here we can get 0.04 as our u value. And the next step is calculating the well function based on this u value. So if it is a certain value, such as 0.04, certain value that you can find from the table, you can directly use table 7.3. So 0.04 will be here. So it gives 2.681. So I matched these values to get 0.04, and the corresponding value for well function is 2.861, which you can see here. And after that, the next step is calculating the drawdown after 1 day, when once the pump started pumping. So S is equal 1 over 4 pi transmissivity 500 times we have flow rate, and it was given as 600 meters cubic meter per day for the first well. So this is 600 times we have 2.681. And from here we can get drawdown as 0.26 meters. And as I mentioned, this is for well 1, and we need to calculate the same drawdown for well 2. Again, let me start with day 1. So here we will get u again. We will use the same equation, and it will be the distance 5 was 500. We have storage coefficient. We have 4, we have 500, and we have 1 for the 1 day. And this gives 0.0625. So as you will see from the table, we actually don't have 0.0625, so that we cannot get this value directly. So in that case, we can use this equation, which is 7.22 in your textbook. So, and we can actually neglect these values because they will be very little. So for example, let's use this part for calculating the well function for well 2 for the first day. So it will be 0.5772 minus ln 0.0625 plus 0.0625. And I want to verify the value in my solutions. So we have 0.5772. And yes, we can get the exact well function value. So it will be 2.257, which you will see here. And similar to previous valve, which is valve 1, we will calculate the drawdown limit, which is S. So we have 1 4 pi, and we have transmissivity as 500. You can follow it from here. We have 1 4 pi transmissivity times Q, flow rate, and valve function. So flow rate was 1400 times 0.257, and this is going to give 0.5 meters. So here we need to create this column, which will give the total drawdown from both of these wells. After 1 day, the pump started pumping. So we had 0.26, and we have 0.5, which gives the total drawdown as 0.76. But if we check the question again, we need to find exceeding a 1 meter drawdown limit. So that we need to find the duration that will be equal to 1. And after that time, we will see drawdown limits higher than 1 meter. So I will let you do remaining calculations by yourselves, because after the first step, we are going to calculate second days. For example, if we assume that 2 days passed. So when we do the same calculations for 2 days, and basically we are going to just change these values. This will be 2, and this will be also 2. And as you can see, the final is 0.97, because 0.33 is coming from the first valve, and 0.65 is coming from the second valve. So we are very close to 1, but we need to do some more iterations. And the question tries day 3. And as you can see, we have 0.36 and we have 0.74 from valve 1 and valve 2, respectively. And as you can see, it gives 1.1 meters, which is higher than what we need. So again, we need to change that. And when we do one more iteration, for example, we can estimate something like 2.5, 2.3. But since the day 2 was very close to 1, which was 0.97, we can estimate something like 2.2. And when we do this, we can directly get 1 meter as the total drawdown limit. So for these calculations, as I mentioned at the beginning, you can use Excel spreadsheets because it may require, I don't know, maybe 6 iterations or 7 iterations to find exact this value. But here I summarized the final results. So in other words, this means that after 2.2 days, pump started, the total drawdown from both wells will be 1 meter. This is question 2, 7.0.6. We need to determine the drawdown at a critical location in a confined aquifer, and it will be affected by 2 completely penetrating wells, and both of them will be pumped at 207 GPM. However, pumping from the second well, which is 279 feet from the point of interest, will start a day and a half after the first well. So this means that, for example, we will have 2 wells, let's say 1 and 2. The well will start pumping, and it will take 1.5 days. And after this 1.5 days, the other one will start pumping. So we need to determine the drawdown at the point of interest 3 days after pumping begins in the first well. The aquifer transmissivity is 450 square feet per hour and the storage coefficient is 0.0005. So since the question says we are going to determine the drawdown at the point of interest 3 days after pumping begins in the first well. So this means that we will have a total of 3 days, which is 74 hours. And also another information, the second well starts, the pumping starts in the second well, and then a half after the first well starts. So this means that after this 1.5 day, we will see the pumping will start in the second well. We also have another information. So it says that the second well is 279 feet from the point of interest. So let me draw this. If this is point of interest, we have well 2 and R2 is 279. This is well 1 and R1 is 22 feet. Okay, so first of all we need to convert the flow rate from GPM to cubic feet per hour because all other values in feet and hours, so that it will be easier. So Q is equal to 449 GPM, and to convert it to hours, from here we will get 1660 cubic feet per hour. Now we need to pay attention to this equation 7.28. So when we have pumps starting at different times, we are going to use this equation to calculate U. And after calculating U, which was a dimensionless parameter, we can calculate well function based on this U value. So the only difference from the previous question, we have different times to start the pump. So let's do for the first well. U1 will be equal to R was 322. We have transmissivity. And here T is 72 because it is the total duration. So U will give 4 times 10 to the power of minus 4. And if we check table 7.3, which we had here, so this is the matching value, which is 7.247. Then we have U value of 4 times 10 to the power of minus 4. So from the table we have 7.247. And based on this value, and this was well function for U1. And now we can calculate the drawdown, which is the same equation we used here. So S1 is equal to 1 4 pi T, which is transmissivity, times flow rate, times well function. And it is 4 pi times 450. We have 1660 times the well function, which is 2.13 feet. Now we are going to apply the same process for well 2. So U2 will be equal this value for 450, and this time we need to check this equation. It says T minus T1, sorry, Ti. So when we look here, we have 3 days in total, so T will be 72, and Ti is equal to this 1.5 days, which is 36 hours. So this basically says that it takes 1.5 days for throughout this pumping process for the second well. So the time for pump well 2, we have 36 hours. This gives 6.01 10 to the power of 4. And again, using table 7.3, we can get well function as 6842. Similarly, we are going to use drawdown equation. And the flow rate is same. The only difference is different well function. And for me here, S2, which is the drawdown from second well, 2.01 feet. So the total drawdown 2 days after the first pumping begins will be equal to 2.13 plus 201, which is 4.14 feet. This is question 3, 7.3.8. A discharge valve penetrating a confined aquifer will be pumped at a rate of 800 cubic meters per hour for 2 days, and then the pumping rate will be reduced to 500 cubic meters per hour. So let me draw something like this. So for 2 days, the flow rate is 800 cubic meters per hour, and for the remaining days, it will be reduced to 500 cubic meters per hour. The aquifer transmissivity is 400 cubic meters per hour, and the storage coefficient is 0.0025. We need to determine the drawdown at a location 50 meters from the pumped well 3 days after pumping gets started. So this means that we will have 1 day, and in total we will have 2 days. And you can check your textbooks for this equation. This is 7.24 and this is 7.25. So according to the textbook, and this is when we don't have constant discharge values. So it means that throughout the period process, we will have different flow rate values. So in that case, you can use this equation. And since we are changing the flow rate, you can also change the equation for U. So let's see what we have. And also for these questions, after the pumping stopped, we will have Qn 0, Q0, 0, and T0 equal to 0, 0. So here when we say N, we have two segments, which is for these 2 days, and this is for 1 day. So N is 2. And Q1 is equal to 800 cubic meters per hour. And Q2 will be equal to 500 cubic meters per hour because we reduced the flow rate. And also T1 is equal to 48 hours. So these are all initial conditions. And let's keep going with the question. So we have this distance. These are just sketch to show what's going on. And we need to determine the drawdown at the location 50 meters from the pumped well. So if this is the pumped well, we will have Q from here. So we will have discharge from this well, and we are going to find the drawdown at 50 meter distance. So for the first segment, which is 2 days of 800 cubic meter per hour flow rate, so we can use this U value. R is 50 square. R is 50 and we have 50 square. The storage coefficient is 0.00025. We have 4. We have 40 as transmissivity. And we have 72 because this time we will have the total duration as 72 hours, which is 3 days. Minus we have T K minus 1. And here when we say K, this will be the first segment. So it says total duration minus T0. So it was 0, so we will use 72 here. And this is going to give 5.43 times 10 to the power of minus 5. Here again you can use equation 7.22, and it is going to give well function as 9.248. Now in the second segment, which we have 500 cubic meter per hour flow rate. So let me write K2. So U2 is also, this was U1. U2 is equal to 50 square times 0.00025. We have 4 times 40 times the time. So based on this equation, it will be T minus T1. So T was 72 and we have T1 is 48, which makes it 24, which you can see here. So we have 1 day or 24 hours for the second segment. But in the first segment, we need to calculate T minus T0, and T0 was 0 as given in the equation explanation. So this is because the pump hasn't started yet, so that we are taking this as 0. And since T is the total duration, it was 72. So we directly use that value. So let's continue with U2. It will be 1.63 10 to the power of minus 4. And again, using equation 7.22. As a reminder, it is this equation. When you cannot find the value from table 7.3, you can directly use this equation. So now it's time to use this drawdown for changing flow rates. So S is equal to 4 pi T times Q1 minus Q0 well function for U1 plus we have the second flow rate for the second segment, so this will be Q2 minus Q1 times well function of U2. So basically we have this outside of the parenthesis, which is here, and we are going to write this equation for both of these segments. So for the first segment, which takes 2 days, we have Q1 minus Q0 times well function for U1 plus we have Q2 minus Q1 times well function for U2. And now let's write our values to find the drawdown. We have 4 pi times 40, and here we have 800 minus 0. We have 9.248. And here Q2 is 500 and Q1 is 800 times sorry, I didn't write this. So the well function for U2 is actually 8.196. So we will have this value here. Okay, so finally we can get 9.83 meters. Now it is question for 7.4.7. We have a little bit different question this time, so let me read the question text. So in this question, we need to find the characteristics of a confined aquifer. And a pump test is conducted at a flow rate of 5.4 cubic meters per hour. The drawdowns are measured at an observation well located 80 meters from the pump well, and these are tabulated below. And we need to determine the aquifer transmissivity, the storage coefficient, and the drawdown after 50 hours. So here in this table, we can see measurements from the observation well for each of these times, and we can see drawdown values. And first of all, you can use Excel, for example, to create this table, which we will have drawdown on the y-axis, and we will have time and on the x-axis. And we can now check these equations below. And a plot of S versus T on the same log paper should give a straight line as shown in figure. So to find the transmissivity, we need to use this equation. And it comes from a log scale, so that we need to deal with log scale for this question. And also in the textbook, it says for any log cycle of t, delta log t is 1. So from this equation, we can get this final equation for transmissivity. And we are also required to find storage coefficient. And from equation 7.4, using log scales, we can get storage coefficient using this equation. And finally, we have drawdown equation, and this is in terms of log scale. So the main reason for using the log scale, when we have a log scale drawdown and time graph, we can get transmissivity, so that we are converting this x-axis to log scale, but we can keep y-axis as linear. So when you create this table, when you create this graph, you will see something like, for example, we have 1 hour, and for 1 hour we will get this point, and for 2 we will get something around here, and for 5 it should be something here, and finally we will have 1.61, which will be here. So let's try to find transmittivity at the beginning. Using this equation. So transmittivity is equal to 2.30 times the flow rate, which is given as 5.4 over 4 pi, and we will have delta S. So according to this graph, the line here is from T1 to T10. So let me write that. And this distance gives the delta S. So to find that, we need to find S value for T is equal to 1 and T is equal to 10. And when T is equal to 10, we have 1.61. And for T is equal to 1, we have 1.09. So this yields to 0.52. And from here, the transmissivity will be 1.9 square meters per hour. And to find the storage coefficient, we need to find T0, which is here. So this is where our best fit line intersects with this horizontal axis. So at this point, we can calculate T0. And when you create this graph based on these values, you will get something similar to this one. And in this graph also, you can find this T0. As I mentioned, you first need to draw a best fit line for all of these points. And when this best fit line intersects with this horizontal line, this is where we have T0. So after calculations, you will get T0 as 0.0082. And from here, the storage coefficient will be 2.25 times transmissivity, which we found as 1.9, times 0.08 over r square, which is the distance, and it was 18. So we have 18 square. From here, we will get 1.08 times 10 to the power of minus 4. And in the question, it says we need to find the drawdown after 50 hours. So drawdown we can use equation 7.4. So drawdown is equal to, and 7.4 is here. This is a drawdown equation for log scales. So we have 2.40, we have 5.4, 4 pi, we have transmissivity, and then log 2.25, transmissivity as 1.9, and T is 50 hours over r square, which is 18, which is the distance, and we have storage coefficient. And as a result, this is going to give 1.9897 meters. Okay, we are here at the final question, question 5, and in your textbook it is 7.5.5. Here we have an information that a factor is pumping 1.55 CFS from a confined aquifer, and its location is 5,660 feet from a fully penetrating river. We also have an observation well, and it is located between the river and the pumped well. And it is 100 feet from the river and 5,560 feet from the discharge well. And it has a drawdown of 0.333 feet. We need to determine the transmissibility of the confined aquifer. So let me first write what we have. So as the question stated, we have a discharge well here. And we have an observation well. It is 100 feet from the river. So let's say we have observation well. And here, this is the river. So this distance is 660 feet. Okay, we have something different in this question. For example, on the right hand side, we can see a figure of the aquifer. And here, it is assumed that there is nothing impacting the aquifers, so that we have an uniform aquifer. This means that we have radially symmetrical drawdown patterns, as you can see here. However, these drawdown patterns are impacted by aquifer boundaries, such as nearby water bodies, such as lakes and rivers. So that in that case, we need to use something different. So basically, since we have a river here, this will impact the aquifer's drawdown patterns. So that to make these problems simpler, we need to create something called hydraulic system. So you can consider this as a representation of the complex aquifer system, and the river here will be recharged. And since we have a recharge, we will create a imaginary well to represent this complexity. So this imaginary well will be placed on the opposite side of the boundary, and it will be located at the same distance from the river. So basically, the discharge well here at this distance, and since to create a hydraulic system to represent this complex aquifer systems, we created this imaginary well. And as I mentioned, it is placed at the opposite location with the same flow rate or same strength, and its location is also same. So it is 5,660 feet from the river. So this is the most different thing from previous question. So let's continue with this hydraulic system. For this kind of questions, we can use 7.12a equation to find the drawdown at point of interest. And we have SOB, which is the drawdown at observation. We have QA, and for example, we can call this QA, and let's call this QB. So we have 2 pi t, and we have ln. Here we have RAO. It is the distance between pumped well and observation well. And on the other part, we have QB, which is the flow rate at this location, which is the imaginary well. And we have our BO, and this is the distance between imaginary well and observation well. And we have RA and RB. And this is the distance from this discharge well and the point of interest. Similarly, it is same for QB. So it is the location from this imaginary well and the point of interest. So let me write all of these values. S will be equal, just a second. S will be equal to 0.333 feet plus, and this is drawdown at the observation as given in the question, plus we have QA, and it was 155. We have 2 pi and T, which is unknown for now, times we have ln. Now we have RAR, which is, this is the distance from pumped well and observed well, and it will be 5,560 because the total distance is 660, and we have this 100 feet difference, so that it will be 5,560. Okay, but the RA, which is the distance from the discharge well and the point of interest, will be same. And we have the same, we have similar values for B. And let's see what we have. This time we have the same flow rate, but since this is opposite, we are going to use minus 1.55 over 2 pi T, and we have ln. RBO is the distance from this imaginary well to observation. So this time we will have 5,660 from discharge well, the point of interest, and we have additional 100 feet to reach to this observation well. So it will be 5,760. And this will be the same because it is distance from imaginary well to the point of interest. And finally, we have this value, and it is assumed as 0. So this means that the drawdown at river is 0. So the only unknown, which is T, or in other words, the transmissibility, can be calculated from this equation, and T will be equal to 0.0262 square feet per second. So if you need to summarize this question, the difference from previous questions or previous discussions, this time we have a river, which is a recharge, and so this impacts the aquifer system, we will not be able to see this symmetrical, radially symmetrical drawdown pattern. Instead, we can create a hydraulic system to represent this complex system, and therefore we can make it simpler. So instead of the river, we are creating an imaginary well at the opposite side of the actual discharge well with the same values, but since it is opposite, it will have minus of the flow rate of this discharge well, and the distance will be same from the point of interest. And once you are done with this imaginary well location, you can just calculate this equation and we can get the transmissibility because it was the only unknown.